Alright, howdy, and welcome to my double lecture on orthogonality. So, last time I was talking about inner product spaces. So, just to review the definition, an inner product on a vector space is an operation that basically takes two vectors inside V and returns a real number, which we denote bracket x, bracket y, satisfying the following conditions. That when you take the inner product of x with itself, you get a number that is greater than or equal to 0, with equality if and only if x is equal to 0. And the inner product of x with y is the same as the inner product of y with x. Further, the operation is linear with respect to the first argument. In fact, it's also linear with respect to the second argument. So alpha x plus beta y inner product with z is the same as alpha times the inner product of x with z plus beta times the inner product of y with z. So an inner product, basically, is a mechanism that generalizes the familiar notion of the scalar product x transpose times y on Rn. So it gives us a way of taking the structure of this particular scalar product and putting it on a lot more kinds of vector spaces. So let's give kind of one of the most important examples, and I started describing it last time, but now I'd like to deal with it concretely. So the example I have in mind is we're going to take our vector space V to be C negative pi to pi, and this of course is the set of continuous functions on negative pi to pi. And we're going to define the following inner product. So if f of x and g of x are two functions on this interval, then the inner product of f of x with g of x is going to be defined to be 1 over pi times the integral from negative pi to pi of f of x times gx dx. And last time I in fact verified that something very similar was actually an inner product. The only difference between the example I did last time and the example I'm doing today is I have this factor 1 over pi here. So here's the reason I have this 1 over pi factor. I'm going to look at a very specific subspace of V. In fact, I'm going to look at the subspace S spanned by the following functions. 1, cosine of x, cosine of 2x, cosine of 3x, blah, 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 cosine of nx. I'm going to note that, of course, 1 is equal to cosine of 0 times x. So S right here is a subspace of my much bigger vector space. And so here's the claim. If I take the inner product of cosine of x, or actually, the inner product of cosine of jx with cosine of kx, this is going to be equal to 1 if j is equal to k and 0 otherwise. So, concretely in the language we introduced last time, cos j of x, cos k of x are orthogonal unless j is equal to k. So let's prove this. To prove this, I'm going to make the following observation, which is that cosine of j plus k times x is equal to cosine of jx cosine kx. So here I'm choosing the addition formula for cosines, minus sine of jx sine of kx. Likewise, we can look at cosine of j minus k times x, and this is going to be equal to, again, cosine jx cosine kx, because I'm using the fact that cosine is an even function, but sine is an odd function, so this becomes plus sine jx times sine kx. So I can add these both together, and I find that cosine of j plus k x plus cosine of j minus k times x, all divided by 2, is equal to cosine of jx cosine of kx. And now I can integrate both sides of this. And the integral goes from negative pi to pi. And I have a 1 over pi on the outside here. So what we find is that this integral is equal to this integral. So this is the thing we want to compute, but now we can compute it in terms of this thing. So you can evaluate this integral right here by appealing to, well, essentially u substitution. You break this into 2 parts and you do the u substitution for each of them. But basically what happens is that whenever you integrate cosine, basically cosine of mx from negative pi to pi, you get 0 unless m is itself equal to 0. So the only way that can happen here, if j and k are positive, is if they're equal. So this is what shows or establishes that this right here is equal to, I guess the other fact you need to know is that the integral of cosine of 0x dx is in fact just equal to pi. So if you divide this by 1 over pi, you get 1. And thus you see that this integral right here is going to be equal to 1 if k is equal to j, and 0 otherwise. So this is basically an example showing how we can use the notion of an inner product on a space that's kind of very, very conceptually different from Rn. But we still have a reasonable notion of orthogonality. So the next thing I want to do is I want to recall something that we proved last time, which is the Pythagorean theorem. And so to recall the statement, suppose x and y are elements of V, are orthogonal elements of an inner product space. Then recall that we defined the norm of x to be equal to the square root of the inner product of x with x. So what happens is the norm of x plus y squared is equal to the norm of x squared plus the norm of y squared. And we proved this in the last lecture. So now what we're going to do is we're going to do something a little different. We're going to try to prove basically a generalization of the Cauchy-Schwarz formula. But in order to do that, we have to introduce some supplementary notions, which are very important in their own right. And so this is the notion of orthogonal projections. And orthogonal projections come in two forms. So you have the scalar projection, and you have the vector projection. Now these are both things that you have seen in some form or another when you've been studying the vector space R2 and R3. And the way they're defined in those vector spaces, in fact, gives you the general definition, but I'm going to spell it out. The scalar projection. So the scalar projection what should I call it? I guess I'll call this, does it actually have a name? Let's call it S proj of a vector V onto a vector U is in fact defined to be the inner product of V and U divided by the norm of U. So this, of course, is a scalar because it's a number divided by a number. Now, the vector projection is just denoted by proj. So the product of v onto u is defined to be, well, first you take the scalar projection, vu, and you divide by the vector u. And what you're going to do is you're going to multiply this by a vector, and your vector is going to be the vector u divided by u. And so this right here gives you the vector projection. And you all have probably seen these in different contexts before. So let me just kind of do an example to remind you how they work. So here is an example. So we're going to take v to be our n. And so our inner product of x and y is going to be the standard scalar inner product. And what we're going to do is we're going to consider the vector v equals 1. Actually, let me write it as a column vector. I'll say x is equal to the column vector 1, 1, 1, and y is equal to the column vector 1, negative 1, negative 1. And what I want to do is I want to compute first the scalar projection of x onto y, and then I want to compute the projection, the vector projection of x onto y. So the scalar projection here is going to be x transpose y divided by the length of y. So you can quickly compute that the length of y, or the norm of y, is going to be the square root of 3. And likewise, the inner product of x with y is going to be negative 1. So this just ends up being negative 1 over the square root of 3. Now we can figure out what the vector projection has to be. It's going to be negative 1 over the square root of 3 times, well, first off I take the vector y and then I divide by its norm. So 1 divided by the square root of 3, negative 1 divided by the square root of 3, negative 1 divided by the square root of 3. And this right here is the vector projection. So you've all done computations like this in the past. Let's do one in the context that we were studying here, namely with respect to a space like this. So how about I set S here to be the span of 1 cosine of x and well, actually, I'm not even going to really bother with that. My vector space V here is the set of continuous functions from negative pi to pi. I'm going to take my vector x here to be, or actually, I'm going to use a different letter. I'm going to take my vector v here to be the function x. So this is just the function that sends, a number to itself. And then my function y here, or u, to be the function cosine of x. And so these are both functions, continuous functions from negative pi to pi. And what I'm going to try to do is I'm going to try to compute the scalar projection of x onto cosine of x. So this will be, first off, I have to compute the inner product of x with cosine of x, and then I have to divide it by the norm of cosine of x. Now here's what I know, that it's given that my inner product right here is 1 over pi times the integral from negative pi to pi of f of x, g of x dx, then I know from the computation I just did that the inner product of cosine of x with cosine of x is in fact just equal to 1. So the norm of cosine of x, which is defined to be the square root of this, is also just equal to 1. So this just ends up being equal to the inner product of x with cosine of x, which is, by definition of our inner product, 1 over pi times the integral from negative pi to pi of x times cosine of x dx. So to compute this scalar projection, what I actually have to do is I have to compute this integral. So let's see how this computation goes. 1 over pi times the integral from negative pi to pi of x cosine x dx. Well, by the, so what is this called? Basically not U substitution, it's basically the reverse product formula from integral calculus. This right here is the same thing as x times sine x evaluated at pi and negative pi minus, oh, sorry, I have to have a 1 over pi here, 1 over pi here, and I'm integrating from negative pi to pi, and here I will have simply sine of x dx. So this right here ends up being, let's see, so sine of pi is 0, sine of negative pi is 0, so this ends up being 0, and then minus the integral negative pi to pi of sine of x dx. And this integral right here, or actually 1 over pi that times this integral right here is also 0. So this just ends up being 0. So going back here, we find that the scalar projection of x onto cosine of x is 0. And thus, these two functions are orthogonal. And likewise, we have to have that the vector projection of x onto cosine of x is just going to be, let's see, well, 0. Now I'm going to use another general fact, or, well, I want to kind of run with this example a bit more because getting 0 is never an interesting answer. So instead, I'm going to stick with my setup. So v here is the set of continuous functions from negative pi to pi. And I'm going to keep my v as the function x, but now I'm going to take my u to be equal to the function sine of x. And we're going to see that something different is going to happen here. And the fact that I'm going to use is with respect to the same inner product, I have that sine of x with sine of x, and this is equal to the norm of sine of x squared is equal to 1. I'm going to leave it to you guys to prove this, so this is an exercise. What I'm going to try to do now is I'm going to try to compute the scalar projection of x onto u, or x onto sine of x. And the computation begins in much the same way. So this will be equal to inner product of x with sine of x divided by the norm of sine of x, which, using this fact over here, just turns out to be the inner product of x with sine of x, which turns out to be the integral from 1 over pi, or the 1 over pi times the integral from negative pi to pi of x times sine x, which is equal to the evaluation of x times cosine of x at pi and negative pi, and then minus the integral, or minus 1 over pi times the integral from negative pi to pi of cosine of x dx. So this quantity right here is 0. This quantity is not. This right here is just going to be pi, actually I should have a 1 over pi on the outside here. So it's going to be 1 over pi and then times negative pi, and then minus negative pi times negative 1. So this just ends up being equal to, after figuring this all out, negative 2. So we compute that the scalar projection of x onto sine of x is equal to negative 2. So now we can figure out what the vector projection has to be. The vector projection of x onto sine of x is simply going to be negative 2 times, well, what you have to do is you have to, according to this formula, take u and divide u by its norm. U in this case is sine of x, and its norm is 1, so it's just going to be negative 2 times sine of x. So we have now computed both the scalar projection and the vector projection of the function x onto sine of x. Now, let me state a lemma. So here's what my lemma is. Suppose that u and v are elements of V, where V is an inner product space. Now what we're going to do is we're going to set u here or we're going to actually set, we're going to write down two different quantities. One of these quantities is going to be x equals v minus the vector projection of v onto u. And then the other quantity is going to be y, and this is going to be just defined to be the vector projection of v onto u. So x plus y is equal to v. Then x is going to be orthogonal to y. So I'm going to prove this. Here's how the proof goes. What we're going to do is we're going to note that the inner product of proj of v onto u with proj of v onto u is the same thing as the inner product of v with u divided by the norm of u, and then times u divided by the norm of u with the inner product of v with u divided by the norm of u times u divided by the norm of u. All of this follows directly from definition. I can now pull this factor and this factor out of the inner product by using the linearity of the inner product. And so this is the same thing as v divided by u divided by the norm of u, all squared, together with the inner product of u with the norm of u with itself. And you can check right here that this term is simply 1, and so this is the same thing as v, the inner product of v with u divided by the norm of u, all squared. So now what we're going to do is we're going to look at the inner product of x with y. So this is the same thing as the inner product of v minus proj of v onto u with proj of v onto u. This will be the same thing as the inner product of v with proj of v onto u minus the inner product of proj of v onto u with itself. Now, fortunately, we've already computed this, so it remains to compute this. So this right here, of course, is inner product of v with u divided by u squared. Whereas this right here is v, and then with what's the definition of this proj? Well, this definition is just inner product of v with u divided by the norm of u times u divided by the norm of u. And what happens is we can pull some factors out of this. So this right here, we can pull this factor out and this factor out. So we have v and u divided by the norm of u. In fact, we can in fact pull the norm of u out from both of these denominators. So we can pull that out as a square. And what's left is v inner product with u minus this thing over here. And now you can see that this cancels with this, and we get 0. So this shows that x and y are orthogonal. So this is one of the main purposes that we use the vector projection for, which is that if we project, v onto u and then we subtract this from v, then in fact what we get is orthogonal to the projection. So this is a very important result. The picture that you should have in mind for it is that if this is v and this is u, then the vector projection is precisely this vector. This is proj of v onto u. And then if we subtract this from this, what we get left over is we get this, and this right here is v minus the projection of v onto u. And so this is the last lemma in kind of geometric form. All right, so given this, we can now prove a general form of Cauchy-Schwarz. So this will be the Cauchy-Schwarz formula. So here's how this goes. The formula states that the inner product of v with u divided by the norm of v times the norm of u is greater than or equal to -1 and less than or equal to 1. And this is true for any inner product space. So here's how this proof goes. What we're going to do is we're going to start by looking at the inner product of v with u, and then divided by the norm of u. So this, of course, is just the scalar projection. But now what I'm going to do is I'm going to note that this is the same thing as the inner product of v minus the proj of v onto u plus the proj of v onto u with u divided by the norm of u. And here's what I learn. First off, the proj of v onto u actually points in the in the same direction as u. That, in fact, is obvious from our formula for a vector projection. Basically, the proj is just a rescaling of the vector u. So consequently, if v minus proj of v onto u is orthogonal to proj of v onto u, it's also orthogonal to u. So we have to have this orthogonality relationship, which means that this right here is the same thing as the inner product of proj, and this will be v onto u with u, all divided by the length of u. So here's what we learn from this. Actually, do I want to do this way? I'm going to change things up slightly here. I'm going to go back here and replace this denominator, u, with v. And everything else I said is still true. Now, this right here is the same thing as the projection of v onto u. So, let's see. I'm actually going to prove this a little bit differently. So here's a somewhat different approach. What we're going to do is we're going to set p here to be the vector that is the proj of v onto u. And then I'm going to consider again the inner product of v with u, in this case divided by the length of u. So this is the scalar projection. This right here is in fact the same thing as the norm of p squared, which is by the Pythagorean theorem equal to the norm of u squared plus, actually no, minus the norm of u minus p. Actually, I should say, I'm sorry. This should be the norm of v squared minus the norm of v minus p squared. This equality right here follows from the Pythagorean theorem. And there's one thing that's slightly off here. This should have been a square in order for this first equality to be true. Now, this right here is less than or equal to the norm of v squared. And what I can do is I can note that the absolute value of both sides, the absolute value of the inner product of v with u, divided by the norm of u squared, is less than or equal to the norm of v squared, which shows that the absolute value of the inner product of u with v divided by the norm of u squared the norm of v is all less than or equal to 1, and from this, the Cauchy-Schwarz formula follows. So this generalizes a lot of the notions that we talked about, basically in the context of R2 and R3, to an arbitrary inner product space. And it also leads us to some other ideas. So, we've already talked about orthogonal vectors. So, namely that x and y in V are orthogonal if the inner product of x and y is equal to 0. What we're going to do is we're going to give a notion of orthogonality not just for a pair of vectors, but for a basis. So let S be the subspace, or be a subspace of V with basis x1 through xk, then the basis is said to be orthogonal is said to be, I guess, an orthogonal basis if the inner product of xi with xj is equal to 0 if I is not equal to j, and alpha, where alpha is not equal to 0 for some alpha, if I is equal to j. So an orthogonal basis is such that if you take any two elements of the basis pairwise and take their inner product, the inner product will be 0 unless they're the same element. And if they're the same element, then you'll get some non-zero number. So there is even a stricter notion of this. So this is stricter. Or I should say, a basis x1 through xk of S is said to be an orthonormal basis if the inner product of xj with xk is equal to 1 when j is equal to k, and 0 otherwise. So the difference between orthogonal is that you're not requiring anything specific on alpha, other than alpha not being 0. For an orthonormal basis, what you require is that the inner product is going to be equal to 1 if j is equal to k. So it's a more specific version of the last one. So these are basically the two most important notions of this chapter. And we're going to study them at length for the rest of today. So here is the first thing I want to kind of note is I want to give some examples of this. So example 1 is going to be very simple. We're going to take v here to be equal to R4. And we're going to look at the standard basis. And the standard basis here, you have the vector 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And we're using the inner product, or the standard scalar inner product, and you guys can check that basically you can literally just see it by inspection that the standard basis is orthonormal. So that example is almost too easy, but in some sense it's the prototype for all the other examples. So here will be our second example. What we're going to do is we're going to set v here to be R3. And I'm going to look at the following basis. So my first vector is going to be 1 divided by the square root of 3, 1 divided by the square root of 3, and 1 divided by the square root of 3. My second vector is going to be 0, negative 1 divided by the square root of 2, 1 divided by the square root of 2. And then my third vector is going to be, so let's see, so I'm going to have, so I think I put a 1/2 here, a 1/2 here, and then I put a negative 1 here. And now I have to look at the length of this thing. So the length will be 1 plus 1/4 plus 1/4. Take the square root of that. So that will just be, it'll be this vector multiplied by 1 over the square root of 3 over 2. So claim this is an orthonormal basis. So let's note that if this is V1, this is V2, this is V3, then we can see right away that the inner product of V1 with V1, which of course is simply the same as the norm squared, is 1 over 3 plus 1 over 3 plus 1 over 3, which is just equal to 1. Likewise, the inner product of V2 with V2 is the same thing as the norm of V2 squared, which is going to equal 0 plus 1/2 plus 1/2. And this will just give me 1. And then finally, the computation that I just had to do in my head when I was writing this down is I have to compute the inner product of V3 with V3. And this just ends up being equal to, so on the outside, I'm going to have 1 over 3 over 2. And then it's going to be multiplied by -1 squared, which is 1, plus 1/2 squared, which is 1/4, plus 1/2 squared, which is 1/4. So you put all this together, you get 1. So each of these 3 vectors has unit length. And you can also see that the inner product of V1 with V2 is equal to 0. The reason that's true is that you take 0 times this, and then you add this times this, plus this times this, but this times this will cancel with this times this. And then you can also likewise see that V2, the inner product of V2 with V3 is 0, because you take this times this, which is 0, plus this times this, which cancels with this times this. And then finally, you have to check that V1 with V3 is 0. And again, that's a calculation. I'll let you guys do it yourself. It's very easy, but it's basically due to the fact that you're going to get 1/2 of this times 1/2 plus 1/2 of this minus 1 times this, and then times whatever this scalar is, but that doesn't really matter. So these 6 computations show that this is an orthonormal basis, and so that is our second example. For our third example, what we're going to do is we are going to look at we're going to let V be the set of continuous functions from -pi to pi. And we're going to set S here to be the subspace generated by the span of E, where E is the basis set, 1 cosine x, cosine 2x, blah, 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 cosine nx. Then, by our earlier calculation, E forms an orthonormal basis for S. And so let me just go back to that computation to remind you of which one I'm talking about. All the way back here, we wrote down our space S, we had our inner product, and what we did is we checked that the inner product of any of these 2 basis elements was 1 if j is equal to k and 0 otherwise. And now we know that this is exactly the condition on this list of vectors needed for it to form an orthonormal basis. So this gives us 3 good examples. So let me now do an example where we have to work a little bit. So, for example 4, I'm not going to give you guys the orthonormal. Well, I'm not going to state the basis in advance. I'm going to have to figure it out. So for example 4, what I want to do is I want to find an orthonormal basis. Actually, I'm going to hold off on this for a little bit. I want to say a few more things before I do this example. So another thing I want to show is a theorem. And this theorem has a name. It's called Parseval's formula. So, suppose x1 through xn is an orthonormal basis for V, then if U is equal to C1 times x1 plus C2 times x2 plus blah 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 Cn times xn, then the inner product of U with itself is going to be equal to C1 squared plus C2 squared plus blah 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 Cn squared. So to see why this is true, the proof is fairly straightforward. So what we do is we basically write down what we know our U is. So it's C1 x1 plus C2 x2 plus blah 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 Cn xn, inner product with itself. And then we use the bilinearity of the inner product to distribute this. And by that I mean we use property 3 and property 2, which shows us that this right here is in fact the same thing as the sum. I equals 1, j equals 1, and both of these are summed to n of Ci, Cj times the inner product of xi with xj. But we've assumed that these form an orthonormal basis, so that tells us that the inner product of xi with xj is equal to 1 if j is equal to I and 0 otherwise. And so this here just ends up being equal to the sum of the Ci squared, where I goes from 1 to n, because all the other terms where I is not equal to j just vanish. So this is a nice formula, and it shows that when you're working with an orthonormal basis, it becomes rather easy to compute the length of functions written in terms of this basis. And this generalizes a property that we already know to be true, at least for the standard basis. Okay. So with that said and done, I want to introduce the notion of orthogonal matrices. So a n by m matrix is said to be orthogonal if the column vectors form an, actually, how about this? I'm gonna do the only, I'll do the general case. If the column vectors form an orthonormal basis. Oh, by the way, my n by m matrix, we're going to call it A. For the column space, are A of A. And this, of course, lives in Rm. So we're using the standard scalar product. So this is an orthogonal matrix. Let's do some examples. So here we can do one pretty easily. We can take A here to be the matrix. This will be a 3 by 2 matrix. The first column vector will be 1 divided by the square root of 3, 1 divided by the square root of 3, 1 divided by the square root of 3, and the second one will be 0, negative 1 divided by the square root of 2, 1 divided by the square root of 2. So we have two column vectors, v1 and v2, and clearly v1, v2 forms an orthonormal basis for the span of v1 and v2, which of course is the same thing as the column space of A. So this is our first example of an orthogonal matrix. So let's do another example. So let theta be a real number. Then we can set A here to be cosine of theta. We put sine of theta here. Negative sine of theta here, and cosine of theta here. Then this will be our first column vector. This will be our second one. And we can check that the norm of v1 is equal to the square root of cosine of theta squared plus sine of theta squared, which of course is just equal to 1. And likewise, we can check that the norm of v2 is equal to the square root of sine squared of theta plus cosine squared of theta, which is again equal to 1. And we can also check that v1 transpose times v2 is simply equal to cosine theta times sine theta minus cosine theta times sine theta, which is equal to 0. So v1, v2 form an orthonormal basis for the row space of A, which of course is just equal to all of R2. So now we have two examples of orthogonal matrices. Let's do another. So, my third example is going to be a class of matrices which are called the permutation matrices. So here's how a permutation matrix is defined. Let E1, E2, En be the standard basis for Rn, and let F1, F2, Fn be a reordering and let me specify that it's an arbitrary reordering of the vectors in E. Then we call the matrix A is equal to F1, F2, Fn, a permutation matrix. And so here's the big claim. Permutation matrices are orthogonal. So let's do some examples of these. The standard basis for R3, of course, is 1, 0, 0, 0, 1, 0, and 0, 0, 1. So that's my E. And we can reorder these in various ways and get different matrices. So for example, we could get the matrix 1, 0, 0, 0, 0, 1, and then 0, 1, 0. We could also get the matrix 0, 0, 1, 0, 1, 0, 1, 0, 0. Or we could leave them all alone and we get the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. We could also get the matrix 0, 0, 1, 1, 0, 0, 0, 1, 0. Or the matrix 0, 1, 0, 0, 0, 1, 1, 0, 0. Or the matrix 0, 1, 0, 1, 0, 0, 0, 0, 1. So I found 6 possibilities, and you can check that this exhausts all possible ways to reorder the set. And all of these are orthogonal matrices. And the reason they're all orthogonal is because we already know that the standard basis is an orthonormal basis. So F1 through Fn, regardless of how it's ordered in the matrix, also has to form an orthonormal basis. So this gives yet another class of orthogonal matrices. All right, so now we're going to prove some key properties. So here is theorem 1. Let Q be an orthogonal N by M matrix, then Q transpose times Q is the M by M identity matrix. So here's how we're going to see this. Q here can be understood as having a sequence of columns. V1, V2, blah, 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 blah. And then Vm. Then over here, Q transpose can be understood as having a sequence of rows. V1 transpose, V2 transpose, blah, 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 Vm transpose. And so if we take the product of Q transpose with Q, we get the matrix that has as entries. Well, up here we're going to have V1 transpose times V1. Over here we're going to have V1 transpose times V2, blah, 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 V1 transpose times Vm. Going down, of course, we're also going to have Vm transpose times V1, and then all the way over until we finally get to Vm transpose times Vm. And now, because we've assumed that Q is an orthogonal N by M matrix, we know that the columns form an orthonormal basis, so that tells us that Vi transpose times Vj is simply going to be equal to 1 if I is equal to j and 0 otherwise, which means the only non-zero things of this matrix right here are precisely the things along the diagonal, and all of them are equal to 1, so this is, of course, the identity M by M matrix. So we often simply write Q transpose Q is equal to I. And this is really one of the most important properties of orthogonal matrices. And we can use it to prove a lot of properties. So, here's my theorem. What we're going to say is, suppose that V is equal to Rn with the standard scalar product so look at the inner product of x and y that's defined to be x transpose times y, and Q is an orthogonal n by n matrix, then the following facts are true. The first one basically follows from the definition of what an orthogonal matrix is. The column vectors of Q form a basis for Rn. Again, this kind of follows directly from definition. The second property is that Q transpose is equal to Q inverse. The third property is that the inner product of x and y is in fact equal to Qx, Qy. So this is a way of saying that if you have two vectors and you apply an orthogonal matrix to them each, it preserves their inner product, and consequently we have the final property, which is that orthogonal matrices, when they're applied to vectors, preserve length. So A essentially follows from definition. Let's look at B. Well, here's what we know. Since Q transpose is equal to the identity matrix, and I'll specify that this is the n by n identity matrix, we can multiply both sides of this equation on the left by Q inverse. So we get Q inverse Q inverse is equal to the identity matrix times Q inverse. But if you multiply anything by the identity matrix, you simply get the thing. And if you multiply Q by Q inverse, you get the n by n identity matrix. So you have Q transpose times In is equal to Q inverse. But then you multiply Q transpose by the identity matrix, you just get Q transpose. So this shows that Q transpose is equal to Q inverse. And likewise, let's look at what happens when we study inner products. So let's look at the inner product of Qx with Qy. Well, this will be the same thing as Qx transpose times Qy. But then this will be the same thing as x transpose Q transpose times Q times y. And as we know, Q transpose times Q is the identity matrix, so this is x transpose times the identity matrix In times y. And you multiply y by the identity matrix, you just get y, so this is x transpose times y, which of course is just the inner product of x and y. So that completes the proof of part C, and that tells us that the matrix Q, when we apply it to a pair of vectors, it preserves the inner product. And then finally, for D, well, the norm of Qx is the same thing as the square root of the inner product of Qx with Qx, which of course by part C is the same thing as the square root of the inner product of x with x, which is just the norm of x. And this completes the proof of the theorem. So now we have a grasp of some of the important properties of orthogonal matrices. And I'm going to do a lot more with them in a minute, but before I do, I want to state the following theorem. So, let S be a subspace of an inner product space V, and suppose S has an orthonormal basis x1 through xk, then consider P, and this is going to be defined to be the sum from I equals 1 to k of, I guess the other thing I need to say is fix a specific vector u in your vector space. And so I'm going to define P as follows. What I'm going to do is I'm going to take my vector u, take the inner product with xi, and then multiply it by the vector xi. Then u minus p is an element of the orthogonal complement of S. So this is going to be the most important theorem that we do because it's going to inform something that we're going to call the Gram-Schmidt process, which will enable us to kind of form orthonormal bases for arbitrary inner product spaces. But before we can do that, we have to prove this. So here's how the proof goes. What we have to show is that we have to show that u minus p, if I take the inner product of it with v, this has to be equal to 0 for all v in S. Now, it suffices to show that u minus p, or the inner product of u minus p with xi, is equal to 0 for each I, precisely because these xi form a basis for S, and if you show that the inner product of xi with u minus p is 0 for each I, then it has to be true for any linear combination of the xi. In particular, it also has to be true for all vectors v. So, in order to do this, let's consider what our expression looks like. U minus p is the same thing as u minus the sum from I equals 1 to k of the inner product of u with xi. Actually, I'm going to use my summing index to be j here. And then it's multiplied with xj, and then I'm taking the inner product of this whole thing with xi. So I can use the linearity of the first argument of the inner product to show that this is the same thing as the inner product of u with xi minus the sum from j equals 1 to k of the inner product of u xj times the inner product of xj with xi. And since we know, of course, that the inner product of xj with xi is going to be equal to 1 if j is equal to I and 0 otherwise, this is just actually going to end up being equal to the inner product of u with xi minus, well, the only term in the sum which is non-zero, which is u inner product of u with xi, which just ends up being equal to 0. And that completes the proof of this theorem. Now, we can address the main problem of this chapter. So here's the main problem. Given an inner product space V, and a basis V1 through Vn for V, how can we produce an orthonormal basis for V? So here's how this goes. The answer is going to be the Gram-Schmidt process. And it gives us a very explicit algorithm that's going to allow us to take an arbitrary basis and perform a sequence of operations modifying it until at the end we arrive at an orthonormal basis. And it's going to tie together all of the ideas that we talked about today, as well as the idea of basically the least squares method of solving linear equations that we talked about in the last lecture. So it's an extremely powerful tool. The algorithm itself is not that hard, and it's going to be based on this theorem that we just proved. So let me explain it first by intuition. So let's suppose we have two vectors. We have V and U. I'm going to call one of them V1, call one of them V2. So the first step, step 1, is to normalize V1 to unit length. And visually speaking, if we do this, then we'll have this picture. So we'll have our V2, that stays the same, but now our V1 has unit length. And then the next thing we do is we compute the vector P from this theorem. And in fact, P here is the, I guess I should say, going back here, P is in fact the least squares projection of u onto S. Now, I haven't proved this, but it might help you understand things intuitively. So, intuitively, in step 2, we're imagining the vector p. In this case, it's not only the least squares projection, it's also the vector projection. So then what we do is we take p and we subtract it from v2 and we get this picture. Again, we still have v1, and v1 has unit length. But now we have v2 minus p. Maybe I'll use a different color here. So in step 2, we replace v2 with v2 minus p. And then in step 3, what we do is we normalize v2 minus p. And this will give us this picture. So this right here is v2 minus p divided by the magnitude of v2 minus p. And this right here is v1 divided by the magnitude. Actually, I've already done that implicitly. So it's just v1, where v1 has unit length. So in going from this picture to this picture to this picture to this picture, I arrive finally at a pair of vectors that are orthogonal, in fact, are orthonormal. They both have unit length, and their dot product to get pairwise is 0. So this is in fact the simplest example of the Gram-Schmidt process. Now I'm going to describe it in full detail. It works as follows. So, let x1 through xn be a basis for an inner product space V. In the first step, we're going to normalize x1, so we're going to set u1 to be equal to x1 divided by its norm. And then, for the second step, we're going to recursively define u k plus 1 to be equal to 1 over the norm of x k plus 1 minus pk times the vector xk plus 1 minus pk, where pk is equal to the sum from I is equal to 1 to k of x k plus 1 ui times ui. So this pk here corresponds to the projection of xk plus 1 onto the subspace of all the previously defined uk's. Then I guess I should say theorem, the resulting UK U1 blah 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 UN form an orthonormal basis for V. So let's go through the proof of this. And the proof is by induction. So the first thing we're going to note is we're going to note that the span of the space generated by x1 is of course equal to the span of the space generated by u1. This is the base case of an inductive proof. So this is obvious because u1 is just a rescaling of x1. And now we assume that the span of x1 through xk is equal to the span of u1 through uk. And what we're going to show is we're going to show that this implies that the span of x1 through xk plus 1 is equal to the span of x1 through u1 through uk plus 1. So here's how this goes. uk plus 1 is equal to alpha times xk plus 1 minus pk, where alpha here is, of course, just the norm. Or actually, it's 1 over the norm of xk plus 1 minus pk. Now, by definition, pk is a linear combination of u1 through uk. So I'm going to note up here that pk lies in the span of u1 through uk. So this in fact shows that xk plus 1 is an element of the span of u1 through uk plus 1. Thus, the span of u1 through uk plus 1 in fact has to be equal to the span of u1, actually I should write it like this, the span of x1 through xk and uk plus 1. But because pk is in the element of this span, we also have, by our inductive assumption, that pk is an element of the span u1, uk. So this in fact is the same thing as the span of x1 through xk plus 1. And this completes the inductive proof that these things, u1 through un, span V. It remains to show that they form an orthonormal set. So here's the other claim that we have to prove. U1 through UK, or U1 through UN, are orthonormal. We already know that they're a basis. So in order to see this, note that UK plus 1 is orthogonal to the span of U1 through UK. In order to see this, we appeal to the preceding theorem, which tells us that if we take a U in our vector space V and we subtract this P from it, we get something in the orthogonal complement. So this in particular shows that Uj is orthogonal to Ui whenever j is greater than I. Now, in particular, for any I and j, orthogonality is a symmetric relation. So in fact, this is true not just for j greater than I, it's true for any j and I. Now, the next thing to observe is that UK plus 1 is defined to be xk plus 1 minus pk divided by the norm of itself. And this, of course, is going to have norm equal to 1. So if we combine this relation with this relation, it follows in fact that the U1 through UN form an orthonormal basis. And this completes the proof of the Gram-Schmidt process. All right, so now what I want to do is I want to do some examples of how the Gram-Schmidt process is used. So here's what we're going to do. We're going to start with the following basis. Give me 1 second. This will be our first example. I'm going to set E here to be the basis. 1, 1, 1, negative 1, 4, 4, negative 1, and then 4, negative 2, 2, 0. So these three vectors form a basis for a subspace of R4. So I'm going to call them V1, V2, V3. And I'm going to apply the Gram-Schmidt process to produce an orthonormal basis for the subspace they span. So our goal is to find an orthonormal basis. For S equal to the span of E. So the first thing I do is I look at my V1 and I compute its norm. And its norm is simply going to be the square root of 1 plus 1 plus 1 plus 1, which is the square root of 4. So if I normalize V1 according to step 1 of the Gram-Schmidt process, I get U1. And U1 is going to be the vector 1 over the square root of 4 times 1, 1, 1. And now I know what my U1 is. In the next step, what I do is I look at my V2, and I have to compute the inner product of V2 with U1. Now, accordingly, this is going to be 1 over the square root of 4, and then multiplied through by, let's see, negative 1 times 1 plus 4 times 1 plus 4 times 1 plus negative 1 times 1. So negative 1 plus 4 plus 4 minus 1. And so I finally get 6 over the square root of 4. And then what I have to look at is I have to look at V2 minus V2, inner product with U1 times U1. And so this is the same thing as 1, 1, 1. Actually, no. Negative 1, 4, 4, negative 1. Minus 6 over 4, and then 1, 1, 1, 1, which just turns out to be negative 1, 1, 1, negative 1, all multiplied through by 10 over 4. And this gives me this vector. And so then finally, to get U2, what I do is I look at V2 minus V2 U1, or V2 inner product U1 times U1 divided by its own length. And if I do that, then I get just the vector negative 1, 1, negative 1, and then times 1 over the square root of 4. So now I have found U1 and U2, and it remains to find U3. So what I have to do is I have to take my V3 and I have to compute its inner product with this, or with this and with this. So V3 inner product with U1, well, we can calculate this to be, let's see, 4 times 1 divided by the square root of 4 plus negative 2 times 1 plus 2 times 1. So that means I just get 4 divided by the square root of 4, which of course is just the square root of 4. I also have to compute V3 inner product with U2, in which case I'm going to get 4 times negative 1 divided by the square root of 4, plus negative 2 times 1, plus 2 times 1, and both of those are divided by the square root of 4, and they cancel. So again, I'm left with negative 4 divided by the square root of 4, which of course is just negative the square root of 4. So given this, I can now note that my P2 here is going to be V3 U1 times U1, and as a vector this is just 1, 1, 1, plus V3 inner product with U2 times U2, which as a vector is just going to be plus negative 1 times negative 1, 1, 1, negative 1. And so this ends up giving us 2, 0, 0, 2. And V3 minus P2 ends up being 2, negative 2, positive 2, negative 2. And to get U3, what I do is I take V3 minus P2 and I normalize it. So I have to compute this length, and if I compute this length and then I divide this by this, you can check that what I get is I get 1, negative 1, 1, negative 1, all multiplied by 1 over the square root of 4. And so I have completed my example and I have found an orthonormal basis. And if I set f equal to 1, 1, 1, 1 times 1 over the square root of 4, and then negative 1, 1, 1, negative 1 times 1 over the square root of 4, and then 1, negative 1, 1, negative 1, all times 1 over the square root of 4, I in fact have a basis with span of f equals the span of my original 3 vectors, but f is an orthonormal basis. Now, let's do one more example for today. Let's let P3 be equal to the set of polynomials ax squared plus bx plus c, where a, b, c are real numbers. And I'm going to define an inner product on this space. By setting it to be equal to P0 times Q0 plus P1 times Q1 plus P negative 1 Q negative 1. And our goal is to find an orthonormal basis for P3. So here's what we do. We're going to use our initial basis as x squared, x, and 1. And the first thing we note is that if we take the inner product of x squared with itself, well, we're going to get 0 times 0 plus 1 times 1 plus 1 times 1, which will be 2. So the norm of x squared with respect to this inner product is the square root of 2, which means our u1 is going to be equal to x squared divided by the square root of 2. The next thing we're going to do is we're going to consider, so this was v1, v2, and v3. Next thing we're going to do is we're going to consider the inner product of v2 with u1. And this is the same thing as the inner product of x with x squared divided by the square root of 2. And so this is going to be the same as 0 times 0 plus 1 times 1 over the square root of 2, and then plus negative 1 times 1 over the square root of 2. And so this will be 0. So in this case, the vector P1, which is just v2 u1, inner product of v2 u1 times the vector u1, is equal to 0. So u2 is going to be equal to v2 divided by its norm. The norm of v2 is equal to the square root of the inner product of x with x. So this is the same as 0 times 0 plus 1 times 1 plus negative 1 times negative 1. And so this just ends up being equal to the square root of 2. So u2 here ends up being x divided by the square root of 2. So now I have found u2 and it remains to find u3. To do this, I have to compute v3, or I have to compute the inner product of v3 with u1. I also have to compute the inner product of v3 with u2. So let's start with this computation. This is the inner product of 1 with x squared over the square root of 2. It's going to be equal to 1 times 0 plus 1 over the square root of 2 times 1 plus 1 times 1 over the square root of 2. And so all of this just ends up being equal to the square root of 2. And then v3 inner product with u2 is going to be equal to inner product of 1 with x over the square root of 2, which is just going to be equal to 1 times 0 plus 1 times 1 over the square root of 2 plus 1 times negative 1 over the square root of 2. So all of it ends up being equal to 0. So P2 here ends up being v3 u1, inner product of v3 u1 times u1, which is just, well, x squared. So what I have to do is I have to set u1 to be equal to 1 minus x squared divided by the norm of 1 minus x squared. So let me do that norm calculation right here. What is the square root of 1 minus x squared normed with itself? Or the inner product of 1 minus x squared with itself. This is just the square root of, so here I'm going to get 1 times 1, and then plus 0 times 0, plus 0 times 0. So I just end up getting 1. So u1 here just ends up being equal to 1 minus x squared. And thus we conclude that x squared divided by the square root of 2, x divided by the square root of 2, and 1 minus x squared form an orthonormal basis for P3. So in my next lecture, I'm going to talk about how we can use the Gram-Schmidt process, not only to find orthonormal bases, but to express an arbitrary matrix in the form of an orthogonal matrix times a matrix R. And this is going to be the basis of a QR decomposition, which is really the most important part of orthogonality. And I'll also give a few more examples on how to do these kinds of Gram-Schmidt calculations. So that is all for today's double lecture, and I will end it right now.